Welcome to the Pyromation Training Lab. In this short video, we'll go over the basics of thermocouple temperature sensors. Temperature sensors are all around us, measuring the temperature of a material, process, or area. You can find them in industrial furnaces for metal heat treating, plastic injection molding machines, chemical refinery cracking units, and in many other applications. The most common type of temperature sensor for industrial applications is called a thermocouple. A thermocouple contains two metal wires made from different materials. They're usually welded together on one end, called the hot or measuring junction. At the other end, the wires are connected to a ceramic terminal block, transmitter, or extension wires. This is called the cold or reference junction. The metal conductors are insulated by a ceramic, magnesium oxide, extruded or braided material, and a ceramic or metal tube or sheath generally protects the sensor from abrasion, corrosion, and/or intense heat. In high-pressure conditions, a drilled bar stock thermowell may be used for stronger protection. So, how does a thermocouple work? The measurement junction is exposed to heat, or occasionally cold, that is different from the reference junction. Because the two metal wires are made from different materials, they respond differently to the heat or chill, creating an electrical reaction called electromotive force, or EMF. This basic concept was discovered by German physicist Thomas Johann Seebeck in 1821 and is still known as the Seebeck effect. The EMF generates a small millivolt output in each leg, and the difference between the two yields a millivolt reading, which is used to calculate the temperature of the process by comparing the difference in temperature between the hot or measuring junction and the cold junction or reference junction. In order to get the most accurate reading possible, the temperature at the reference junction has to be confirmed. Also, the lead and thermocouple extension wires must have no other contact points. The millivolt signal passes through the terminal block or connectors and continues along the thermocouple extension wires to a display or programmable logic controller unit, PLC for short. At this point, the signal is converted to the temperature reading. The thermocouple extension wire must be made of the same metallic material as the thermocouple itself in order to maintain the integrity of the EMF signal. The thermocouple wire can be connected to the display in many ways, using plugs and jacks, spade lugs, ceramic terminal blocks and enclosures, and more. The signal can also be sent through a temperature transmitter, which converts the signal to milliamps and routes it along copper wires to the display or control unit. Using a temperature transmitter is an ideal option for longer distances because it amplifies the signal and can use economical copper wires instead of more expensive thermocouple extension wires. Wireless transmitters are also available at greater expense. The thermocouples come in a variety of types, each with conductors made of different metal alloys. This allows us to measure a wide range of temperatures in many different environments. Finding the right thermocouple for the job is generally determined by application conditions, data requirements, application function, and cost. This chart shows the temperature ranges for the most common types of base metal thermocouples, each identified by a letter designation. For extremely high temperatures, noble metal thermocouples are necessary, but they are extremely expensive. Thermocouple types are usually identified by the colors of the conductor insulators and the outer jacket. This chart shows the North American color codes. Keep in mind that color codes for other regions are slightly different. If the thermocouple doesn't have a color-coded insulation or jacket, the type can usually be identified by the connection or leads. Type K and J can be identified by measuring the magnetism in one of the legs. Each thermocouple type has known millivolt values at specific temperatures. These values are based on the cold junction being at 0 degrees Celsius or 32 degrees Fahrenheit. In a metrology lab, thermocouple material is calibrated using an ice bath in a controlled environment. However, cold junctions don't typically operate in those chilly conditions, so a cold junction compensation is needed to calculate a correct temperature reading. These calculations are performed at the PLC or temperature transmitter. The thermocouple's length doesn't have any effect on the voltage reading, but can impact the signal integrity due to electrical noise or interference. So, how do you choose the right thermocouple length for a specific operation? Start with the immersion distance. A thermocouple should have an immersion length of at least 10 times the outside diameter of the thermocouple's outer jacket, protection tube, or thermowell. Determining the right immersion distance is a good start, but there are other factors to consider when choosing the correct thermocouple. Thermocouples are constructed with various wire diameters depending on requirements. Large diameter wires are more durable and will last longer at higher temperatures, while smaller diameters provide greater sensitivity but wear out more quickly. Thermocouple types are considered accurate within a standard tolerance range. For example, Type K will provide an accurate temperature reading plus or minus 4 degrees Fahrenheit or 0.75% of reading, whichever is greater, from 32 degrees to 2300 degrees Fahrenheit. If you need greater accuracy, you can request a thermocouple made with special tolerances material to reduce the margin for error. For example, a Type K made with special tolerances material cuts the margin of error to plus or minus 2 degrees Fahrenheit or 0.4% of reading, whichever is greater. Although the conductors remain the same material, the calibration of the conductor material meets more precise specs. Of course, there is a cost associated with special materials. Along with thermocouple type, length, and tolerances, you need to determine the best hot junction construction for your application. There are 3 basic types of hot junctions: ungrounded, grounded, and exposed. Each has its own advantages and disadvantages. In an ungrounded thermocouple, the conductors are surrounded by insulation and never touch another surface. This provides additional protection, is less susceptible to outside interference or noise, and can be used in almost any corrosive or abrasive condition. It is, however, marginally slower in response time. A grounded thermocouple is designed with the conductors touching a metal surface, generally the inner surface of a metallic sheath covering the tip. This design provides a faster response time but is still good for use in abrasive or corrosive applications. What's the catch? Grounded thermocouples are susceptible to noise. An exposed thermocouple is exactly what it sounds like. The conductors are out in the open with no insulation or metal sheath for protection. Exposed thermocouples offer the fastest response time, but can't be used in corrosive or abrasive applications. Thermocouples are usually less expensive than other temperature sensors and are more rugged. While they can be slightly less accurate, thermocouples can measure a wider range of temperatures. Pyromation has the expertise and experience to help you select the right thermocouple for your application. So, there you have it. As you can see, thermocouples are a fairly simple technology that provide critical temperature information in a wide range of industrial applications. This concludes Pyromation's training lab on thermocouples. If you like this video, please click the thumbs up button below. While you're at it, go ahead and subscribe to the Pyromation Training Lab. It's free and guarantees that you won't miss the next chapter of this instructional series.